Revathi ma'am.
Yes, sir.
Ma'am, can we start?
Sure, sir.
Okay. Good morning, participants. Welcome back to the 11th day of the AICT sponsored FTP program. Today we have with us our resource person, Professor R. Revathi, to share their experience and technicalities with us in the field of electric vehicles and powertrain. On behalf of the management, principal, and organizing team, we welcome Professor R. Revathi ma'am for this session. So to tell a few words about ma'am, she has completed her B degree in Electrical and Electronics Engineering from LLR College of Engineering Technology and her Masters in Power Electronics and Drives from Kumaruru College of Technology and a PhD degree from Anna University, Chennai. Her area of interest includes digital logic circuits, control system, and power electronics. She has published around 50 papers in various conferences, journals, and she has been active reviewer in most of these journals. She has guided various projects under her belt, and many have won laurels to the organization. For example, as piezoelectric bike, rain detector using Arduino, energy monitoring and management for smart campuses, development of GSM-based automatic trip control system for energy management with instant billing, automatic opening and closing of doors through Android application using Arduino Uno, and few she has got grants from Tamil Nadu State Council for Science and Technology, Indian Society of Technical Education, Council of Scientific and Industrial Research towards organization of various seminars. And recently she was appreciated with the 35 project participation. Ready to market display at Euro in Tech 2020, and she is an active member of IEEE transactions and a reviewer of IEEE on power systems and IET. At this juncture, I take this opportunity to welcome her once again, and I request her to take over the session. Ma'am, you can take over the session.
Yes, sir. Thank you for your brief introduction. So, good morning, one and all present here. Am I audible?
Yes, ma'am, you're audible.
Okay, sir. So, on behalf of the department and organizing team, I welcome you all for this 11th day FDP on design and operational perspective of electric vehicles with distributed energy sources using cyber physical systems. Today, I have given the topic optimization of powertrain for maximum energy economy. As Ravi sir introduced, myself R.Revathi, working as an assistant professor in the Department of Electrical and Electronics Engineering, KPR Institute of Engineering and Technology, Arasur, Coimbatore. So for the past 10 days, we are learning electric vehicles and what is the need for electric vehicles and what are the types and what are the benefits, what are all the soft computing algorithms and battery management system and so on. So for a glimpse, why to think alternative mode of transportation? Here, the development of internal combustion engine vehicle is one of the greatest achievements in the modern technology. Here, the large number of automobiles in use around the world poses serious problems for the environment as well as for human life. Air pollution, global warming, and the rapid depletion of the Earth's oil resources. So this leads to alternative mode of transportation. So now the need is high efficiency, clean and safe transportation. So this is the chart in the year 2018. So that is India's total vehicle population. So around 320 total vehicles, 73 percentage of uh, quantity belongs to two-wheelers, and around 13 percentage belongs to the vehicles like cars, jeeps, and taxis. and around 1 percentage belongs to buses, that is for public transportation, and around 5 percentage is belongs to goods and vehicles. Then 8% belongs to other vehicles. It is the source taken from motor vehicles, that is Statistical Yearbook India 2018, under the Ministry of Statistics and Program Implementation, Government of India. So as the vehicles users are increasing day by day, so we have to choose alternative mode of transportation. So that is electric vehicle or hybrid electric vehicle. So these are the greenhouse gas emissions, that is pollutants, that is carbon monoxide, carbon dioxide emissions, then nitrous oxides, then unburned hydrocarbons are released from the conventional vehicles. So medium-sized car for 10 years with fuel consumption of around 9 to 10 kilometer per liter will produce approximately carbon monoxide, that is around 325 kilogram of quantity. Then unburned hydrocarbons is around 36 kilogram. Then nitrous oxides is around 47 kilogram. Then carbon dioxide emission is around 44,000 kilogram. So this leads to environmental impact. So this leads to global warming. So this amount of exhaust gas emission will create about 1 billion meter cube of polluted air. So in order to protect our environment, we have to think alternate mode of transportation. Green technology. So air pollution and energy crisis have triggered an upward trend in developing green powertrains for vehicles and construction equipment. Excavators, bulldozers, forklifts, loaders are the most widely used construction equipments, as we all know, and therefore their energy utilization and emissions have drawn much attention to green technology. So instead of using fuel vehicles, they are going for electric vehicles. So green vehicle technology. So in the year 1905 to 2020, spark ignition engines and compression ignition engines came into existence, as we all know. So from the year 2021 to 2030, HCCA, that is homogeneous charge compression ignition, and RCCA, that is reactivity controlled compression ignition, came into picture. So what is HCCA? Homogeneous charge compression ignition is a short form of HCCA. It is a form of internal combustion in which well-mixed fuel and oxidizer, that is typically air, are compressed to the point of auto-ignition. As in other forms of combustion, this exothermic releases energy that can be transformed in an engine into work and heat. So in the case of HCCA. So it combines the characteristics of conventional gasoline engine and diesel engines. So RCCA, that is reactivity controlled compression ignition. So during this combustion, well-mixed low reactivity fuel and oxidizer, that is typically air, are compressed but not reaching auto ignition. Later still, during compression cycle, high reactivity fuel is injected to form a local mixture of low and high reactivity fuel. Finally, the whole fuel charge is ignited near top dead center of the piston by injection of high reactivity fuel. So this combustion process requires two different fuels in RCCA. That is, low reactivity fuel gets injected into the intake ports with low pressure during the intake stroke. High reactivity fuel gets injected into the cylinder with high pressure at the end of compression stroke. So this comes to HCCA and RCCA features. So after 2030, hybrid electric vehicle come into picture. So it combines the features of electric motor and HCCA engine. So after that, so electric vehicle which comprises of battery as well as fuel cell. So battery in the sense, so the cost wise it will be expensive. So after that we are eliminating the battery and the electric vehicle is introduced with fuel cell and solar energy. So that is renewable integration is into coming into the picture. Then after that, the electric vehicle, which is purely comprises of solar energy and renewable sources. So this we have to think of, and the research is going on this topic, electric vehicle with renewable integration. So this is the EV evolution. So in the year 1769, origin of steam engines came into existence. So in the year 1806, first ICE engines on fuel gas is introduced. After that, in the year 1860, first successful gas-driven engine is coming into picture. After that, 1893, first gasoline-powered car is introduced. So during the period 1890 to 1924, the period is said to be golden age of EV, that is electric vehicle. So here the peak production of EV is introduced in the year 1912. And after 1924, the domination of gasoline cars came into existence. So it dominated the market. So the EV becomes depleting. So it gets disappeared after 1924 and 1960. So after 1960, limited production of EVs are coming into picture. So after 1972, the 1990, the first generation of EVs introduced and incorporated technology into EV design. After 2000, the hybrid eclipse of EV an increasing level as gas supplies demand. So this is the evolution of electric vehicle. What is the need for hybrid and electric vehicles? Zero harmful emissions, as we all know, that is better for environment. Scarcity or depletion of fossil fuels. The reduction of noise pollution, maintenance less, then more efficient and cost-effective solution. So these are the features and these are the advantages why we are going for hybrid and electric vehicles. Vehicles energy consumption. So energy required is the product of volts and ampere drawn per kilometer. So that is measured in kilowatt hour per kilometer. So the energy consumed by the two-wheelers is around 100 to 50 to 100 watt hour per kilometer. So in between 50 and 100 watt hour per kilometer. So the energy consumption of car, that is four-wheelers, is around 150 to 250 watt per kilometer. The energy consumption of medium commercial vehicles is between 300 to 400 watt hour per kilometer. So the range of vehicle depends not mainly on energy consumption in addition to speed, pack kilowatt hour rating, driving conditions, hills, aerodynamics, vehicle weight, temperature, driving styles, and other several factors. Here the distance is measured in kilowatt hour of pack or watt hour per kilometer or kilometer. So this is the details of the vehicle's energy consumption. So what are the forces acting on an automobile? As we all know, there are some forces acting on an automobile. So there is aerodynamic drag, rolling friction, inertial force during acceleration, and forward force. So the forward force is the summation of rolling resistance, aerodynamic resistance, inertial resistance, and gradient resistance. So vehicle movement. So powertrain movement. So here the tractive force plays a major role in the vehicle movement. So that is denoted by Fp. This the tractive force in the contact area between tires of the driven vehicles on the road surface propels the vehicle forward. So it has to oppose the forces acting on the automobiles. So that is the tractive effort Fp. So while the vehicle is moving, there is the resistance that tries to stop its movement. So the resistance usually includes tire rolling resistance, aerodynamic drag, and uphill resistance. So here high pressure is applied and here low pressure is applied as the vehicle is moving forward. So this is the electric vehicle. Here the electric vehicle is comprises of electric traction motor, that is EM, all-round controller, that is conditioning unit or controlling unit, then DC-DC converter unit, then thermal system for cooling and heating purpose, and for battery pack for battery management system, then charging port, then transmission system, onboard charger, then battery with auxiliary components. So what exactly is an HEV? That is hybrid electric vehicle. So it anticipates future technologies of energy sources. The term hybrid vehicle refers to a vehicle with at least two or more sources of power. A hybrid vehicle indicates that one source of power is provided by the electric motor. The other source of motive power can from a different technologies, but is typically provided by an ICE, that is internal combustion engine, that is designed to run on either gasoline or diesel fuel. So hybrid electric vehicle is a vehicle in which propulsion energy is available from two or more types of energy resources, and at least one of them can deliver electrical energy. So EV introduction. Switching from one to the other at the proper time yields a win-win in terms of energy efficiency that results in greater fuel efficiency and also reduces the power consumption. So hybrid vehicle, it uses two or more distinct types of power. Electric motor that is capable and more efficient to produce starting torques. Combustion engine, it is better for maintaining high speed. So this is the electric vehicle features. So these are the components in electric vehicle: motor, battery, transmission system, motor controller, and vehicle controller. So motor, we all know. So electric motor is an device which converts mechanical energy into electrical energy. So the battery is used for energy storage. So the converted energy is stored here for later purpose. The transmission system, so it has to deliver the power to the wheels. The motor controller, so the controller or conditioning unit plays a vital role in conditioning the power to all the accessories, that is headlight, starting from headlight to the steering wheels. Then vehicle controller, it also adds a main characteristics and introduces the strategies to achieve charge sustainability with battery life expectancy in addition to these features. So these are the vehicle components. So inverter, so as we all know, it converts DC into AC. So here battery, it is used for energy storage purpose. So here motor or generator, so motor which converts mechanical energy into electrical energy. So as well as the generator. So modern and hybrid electric vehicles. So hybrid cars rely on the regenerative braking system. So when a standard combustion engine car brakes, a lot of power is lost because it dissipates into the atmosphere as heat. Regenerative braking means that the electric car is used for slowing down the car, and it essentially collects this power and uses it to help recharge the electric batteries within the car. So this is used for stopping the car, that is for slowing down the speed. This development is believed to have progressed hybrid vehicle manufacture significantly. A configuration of the regenerative system for construction equipment and energy management strategy are being proposed to reduce the fuel consumption. So here, in addition to fuel consumption, the fluctuation of the fuel cell as well as battery state of charge are also minimized in this uh, electric vehicle or hybrid electric vehicle to save the operating cost and prolong the lifetime of the energy storage devices. The feature of HEV. Since petroleum is limited and someday it will be running out of the supply, the market may develop for solar powered EVs of the size of a scooter or golf cart. Since hybrid technology appears to heavy vehicles, hybrid buses and hybrid trains will be more significant. EV charging infrastructure is the need of tomorrow across the globe. So integration of this infrastructure to Internet of Things with smart sensor technology will connect together the city services, city transportation, and city citizens. This smart system will help in planning of city services, city transportation, and will help citizens in their day-to-day life. So electric vehicle with IoT technology and with smart sensor technology will help citizens in their day-to-day life. Pros and cons of the hybrid electric vehicle. So conventional vehicles with internal combustion engine. So there are some advantages in conventional vehicles. So there is good performance and long operating range. There are some of the disadvantages, that is poor fuel economy and environmental pollution. Poor fuel economy. Engine fuel efficiency characteristics are mismatched with the real operation requirements. Dissipation of vehicle kinetic energy during braking, especially while operating in urban areas. Low efficiency of hydraulic transmission in current automobiles in stop and go driving patterns. So these are some of the disadvantages in conventional vehicles with internal combustion engine. The next comes our battery powered electric vehicles, that is EV. There are plenty of advantages when compared to conventional vehicles. That is high energy efficiency and zero environmental pollution, as we have discussed already. There are some disadvantages, that is performance and operation range per battery charge is far less. So these are the advantages and disadvantages of conventional vehicles and battery powered electric vehicles. Conceptual illustration of a hybrid electric drivetrain. So here, although the electric tractor shares many common structural features with a common electric vehicle, there are some significant differences between the two drivetrains. Particularly, the electric vehicle layout is powered by the energy system, that is, by the battery. So the energy system can contain the storage battery in a pure electric tractor or the internal combustion engine, generator, battery, supercapacitor, and so forth in a hybrid electric tractor. So the electric motor provides the mechanical power for the drive wheel and power takeoff shaft. So here the power takeoff shaft joins with the electric motor via the clutch. When the tractor only drives the uh, agricultural implement, the clutch decouples the mechanical connection between the power takeoff shaft and the drive wheel, which makes the mechanical power flow to be dependent of each other. The gearbox transmission system can transform the dynamic power performance field of the drive wheel via the gear shifting operation of the driver. And here the gearbox transmission directly transmits the mechanical power to the power takeoff shaft, which can make the rotating speed of power takeoff shaft match with the either the rotate speed of the electric motor or the forward velocity of the electric tractor. Here the main drive acts as a differential mechanism and final reducer of the transmission system. By stepping on the accelerator pedal, the driver can control the electric motor through electrical adjustments of the motor controller. So there are two types of load force exerted upon the electric tractor. One is driving force and the other is pulling force. So these are the conceptual illustration of a hybrid electric drivetrain. So here, in order to maintain movement, vehicles must produce power at the wheels to overcome aerodynamic drag, that is, air friction of the body surfaces of the vehicle coupled with pressure forces caused by the airflow. Then rolling resistance. Then resistive gravity forces associated with climbing a grade. Further, to accelerate the vehicle must overcome its inertia. So here the most of the energy expended in the acceleration is then lost as heat in the brakes when the vehicle is brought to a stop. The vehicle must provide power for accessories such as heating fan, lights, power steering and air conditioning. Finally, the vehicle will need to be capable of delivering power for acceleration with a very little delay when the driver depresses the accelerator, which may necessitate keeping the power source in a standby or energy using mode. Here, although the fuel-driven energy source on a hybrid generally will be of low power and weight than the engine in a conventional vehicle, total hybrid weight is likely to be higher than the conventional vehicle, but it replaces because of the added weight of the storage device, electric motors, and other components. This depends, of course, on the storage mechanism, the vehicle performance requirements, and so forth. Although individual electric drivetrain components tend to be quite efficient for one-way energy flows, in many hybrid configurations, electricity flows back and forth through components in a way that leading to cascading losses. Or the sum of the components may be forced to operate under conditions when they have reduced efficiency. For example, like internal combustion engines, most electric motors have lower efficiency at the low speed, low load conditions often encountered in city driving. So here control strategy is introduced for optimization of powertrain. So here most of the patterns combines the power flows to meet the load requirements. So the various possible ways of combining the power flow to meet the driving requirements are powertrain 1 alone delivers power. Next, powertrain 2 alone delivers power. Next, both powertrain 1 and 2 deliver power to the load at the same time. Next, powertrain 2 obtains power from load, that is through regenerative braking. Next, powertrain 2 obtains power from powertrain 1. Next, powertrain 2 obtains power from powertrain 1 and load at the same time. Next, powertrain 1 delivers power to load and to powertrain 2 at the same time. Next, powertrain 1 delivers power to powertrain 2 and powertrain 2 delivers power to load. Next, lastly, the powertrain 1 delivers power to load and load delivers power to powertrain 2. So there are generic concept of a hybrid train and possible energy flow route is shown here. So the load power of a vehicle varies randomly in actual operation due to frequent acceleration, deceleration, and climbing up and down the grades. Here the load power can be composed into two parts, steady power and dynamic power. So next comes the EV architecture. As we have discussed already, so the EV architecture consists of motor, electric motor, transmission system, inverter, DC to DC converter, onboard charger, battery, battery management system, EMS energy management system, then controller area network, DC-DC converter, then wireless charger, pump and other auxiliary devices. So this is the EV architecture. So here fast charging station is also included. So electric powertrain challenges. So what are the challenges in electric powertrain? So there is cost, weight, size, life of the battery, range, disposal or recycling, power electronics efficiency. So these are the powertrain challenges in electric vehicle. So classification of hybrid electric vehicle. So there are four types of hybrid electric vehicle. That is series parallel hybrid, and complex hybrid. So here, series hybrid system. Here, series hybrid system consists of fuel tank, internal combustion engine, generator, battery, power converter or conditioning unit, electric motor, and flexible transmission system. In case of series hybrid system, the mechanical output is first converted into electricity using a generator. Next, the converted electricity either charges the battery or can bypass the battery to propel the vehicles via the motor and the mechanical transmission system. Conceptually, it is an internal combustion engine assisted electric vehicle. The advantages are mechanical decoupling between the internal combustion engine and driven vehicles allows the IC engine operating at its very narrow optimal ratio. So the next advantage is really ideal torque speed characteristics of electric motor make multi-gear transmission unnecessary. So these are the advantages of series hybrid drivetrain. So it has some of the disadvantages here. The energy is converted twice, mechanical to electrical and then to mechanical. This reduces the overall efficiency of the system. Two electric machines are needed and a big traction motor is required because it is the only torque source of the driven wheels. It is used in heavy commercial vehicles, military vehicles and buses. The reason is that large vehicles have enough space for the bulky engine or generator system. So this is about the series hybrid system. Next comes parallel hybrid system. So it allows both ICE and electric motor to deliver power to drive the wheels. Since both the internal combustion engine and the electric motor are coupled to the drive shaft of the wheels via two clutches, the propulsion power may be supplied by internal combustion engine alone, by electric motor only, or by both internal combustion engine or by the electric motor. The electric motor can be used as a generator to charge the battery by regenerative braking or by absorbing power from the internal combustion engine when its output is greater than that required to drive the wheels. There are some of the advantages are both engine and electric motor directly supply torque to the driven wheels and no energy from conversion occurs. Hence, energy loss is less when compared to series hybrid drivetrain. Next advantage is compactness due to no need of the generator and smaller traction motor. There are some of the drawbacks in parallel hybrid drivetrains. Here, the mechanical coupling between the engines and the driven wheels, thus the engine operating points, cannot be fixed in a narrow speed region. The mechanical configuration and the control strategy are complex when compared to series hybrid powertrain. So due to its compact characteristics, small vehicles use this type of parallel configuration. Most passenger cars employ this configuration. So next, series parallel system. In series parallel hybrid configuration, it incorporates the features of both series and parallel hybrid electric vehicles. However, this configuration needs an additional electric machine and a planetary gear unit making the control complex. So it combines both the features of hybrid, series hybrid and parallel hybrid configuration. Next, complex hybrid. So it involves a complex configuration which cannot be classified into the above three kinds. The complex hybrid is similar to the series parallel hybrid since the generator and electric motor is both electric machines. However, the key difference is due to the bidirectional power flow of the electric motor in complex hybrid and the unidirectional power flow of the generator in the series parallel hybrid. The major disadvantage of complex hybrid is higher complexity. So this is about the classification of hybrid electric vehicles. So next comes our optimization of hybrid electric vehicles. So hybrid electric vehicles have emerged as an alternative to reduce fuel consumption and pollutant emissions while maintaining vehicle performance. Here, the first attempts to optimize HEV's performance focused on the proper selection of powertrain components such as the internal combustion engine, ICE, electric motor, battery pack, and transmission system. The recent work improves the control strategy which regulates the energy flow between prime movers, transmission, batteries, and wheels to accomplish driver demand. Here, the control strategy is regulating the energy flow between these components to accomplish the driver demand. The main input control variables are power demanded, vehicle speed, and the battery SOC, that is state of charge capability. Here, the control map is based on the basic engine operating line and transmission kinematics. So, the engine, battery, electric motor, and transmission system are taken into account for optimizing these parameters. Powertrain components. So, any vehicle powertrain is required to develop sufficient power to meet the demands of the vehicle performance. So, it carries sufficient energy on board to support vehicle driving in the given range. So, it demonstrates high efficiency and emit few environmental pollutants. Here, the optimization is a study where dynamic characteristics of a commercial vehicle are used with the powertrain parameters and control strategy variables, which is subjected to multi-objective genetic algorithm. So, these are the powertrain components. So, in the electric vehicle, powertrain configuration. Here, the powertrain configuration comprises of electric propulsion subsystem, energy source subsystem, auxiliary subsystem, and steering wheel. So the electric propulsion subsystem consists of vehicle controller, electronic power converter or power conditioning unit, electric motor, then flexible transmission system, and the wheel. So this is the propulsion system. So energy source subsystem comprises of energy management unit, energy source, and energy refueling unit. So these comprises of energy subsystem. Auxiliary subsystem comprises of auxiliary power supply, power steering unit, climate control unit. So this is the auxiliary subsystem. So in conventional mode, the electric motor is not used. The internal combustion engine supplies all required power to accomplish the tri-cycle demand, and all excess energy generated is sent to charge the batteries. The internal combustion engine is engaged to the continuous variable transmission system. Here the energy passes to the ring of the planetary gear set and through the simple train, and the ring of the powertrain system is connected to the differential which distributes the energy to the wheels. But in electric mode, the power to move the vehicle is provided by the batteries through the electric motor. Here, the electric motor is engaged to the carrier with a mechanical reduction, which energy split to the sun and the ring gears of the planetary gear set. Here, the energy that goes to the sun is also transmitted to the ring through the continuous variable transmission onto the simple train. The energy transmitted to the ring passes to the wheels through the differential system. But in regenerative braking, the energy flow inverts and the electric motor works as generator, sending back part of the vehicle's kinetic energy to the batteries. And the configuration is series hybrid and parallel hybrid. In series hybrid mode, the vehicle works as an electric mode, but instead of using the battery energy, the internal combustion engine through the alternator provides electrical energy to the electrical motor and recharges the batteries. This mode works when the rotational speed of the internal combustion engine is below the adequate efficiency to be connected to the wheels. Hence, it is used to increase the battery state of charge, that is, to monitor the state of health parameter of the battery. Next configuration is parallel hybrid. In parallel hybrid mode, the internal combustion engine and electric motor work together. The internal combustion engine is connected to the shaft of the sun gear and defines the rotational speed of the ring gear through the continuous variable transmission on the simple train. As the internal combustion engine sets 2 degrees of freedom for the planetary gear system, the rotational speed of the arm is defined, and therefore the angular velocity of the electric motor and the rotation speed of the wheels. In this mode, the electric motor adds torque to accomplish the driving cycle demands. So this is about the powertrain configuration. So series hybrid and parallel hybrid configuration. So this is the performance characteristics of a vehicle. So this chart shows the ideal characteristics of a vehicle. So look into this. The x-axis is speed and the y-axis is motor power or torque. So here at particular speed, the the torque and power is maximum, and after that speed, so it decreases gradually. The torque decreases gradually. While coming into power, so at particular speed, the power becomes constant. So this is the ideal characteristics of an electric vehicle. So typical performance characteristics of gasoline engines, that is ICE engines. So here the characteristics are poor. So as we have already seen in the cons of ICE, so the torque and power is not up to the performance level. So it is not up to the expected level. So also the fuel consumption is high when compared to electric motors. So the typical performance characteristics of electric traction motor, it looks similarly ideal characteristics of a vehicle. So it is recommended to use electric vehicles for the future purpose. So here the tractive effort versus vehicle speed with the traction motor of 3-gear transmission. So here the vehicle speed is taken along the x-axis and tractive effort, that is FT, is taken along the y-axis. So here the ABC curve shows the first gear operating region. The curve DEF shows the second gear operation region, and the curve GFH shows third gear operation region. So here the motor speed ratio is taken as twice. So this is the tactic effort, and this curve, that is this belongs to rolling resistance as well as aerodynamic drag. So this is the H is the maximum speed of the vehicle. So this is the performance characteristics of a vehicle while considering tractive effort versus vehicle speed characteristics. So next, powertrain schematic. So the powertrain of a hybrid electric vehicle must be capable of managing energy from two power sources and deliver it to the wheels. So this is analyzed here. And so this is the block schematic of the powertrain components. So here it consists of wheels, differential system, internal combustion engine, planetary gear system, then continuous variable transmission, then simple train, then electric motor, then power conditioning unit, and the energy storage system, that is battery. So these are the block schematic of a powertrain components. So here, due to the CVT's belt force limitations, it is a design priority to minimize the strength to which it is submitted. So it is the inverse relationship among F belt, N, and CVT alike. It can also be observed that an increase in tau CVT causes an increase in F belt. So this is the power train schematic of an electric vehicle. So this is the powertrain parameters and fuel economy. So here speed is taken along the x-axis and power is taken along the y-axis. Here the curve Pmax corresponds to the top power of the internal combustion engine that can deliver data. So here the curve P minimum is correspond to the minimum power to start the internal combustion engine mechanically connected to the wheels. This control parameter seeks to improve fuel economy by shutting down the internal combustion engine under low power demand conditions. Curve PEM represents the maximum power the electric motor can deliver as a function of the vehicle's speed. Here, curve P1 is a function of E that gives the minimum power that the internal combustion engine can deliver working on its basic engine operating line. Curve P2 is a function of V that gives the maximum power the internal combustion engine can deliver working on its battery engine operating line corresponding to maximum tau CVT. Then curve P3 is the sum of curves P2 and the nominal power of the electric motor resulting in the total available power at the vertical line V minimum represents the minimum required velocity to connect the internal combustion engine to the wheels. It passes through the intersection of P minimum and P2. And curve VE represents the top speed selected for which the electric motor can deliver power. Here, curves P1 and P2 are explained by battery engine operating line of the internal combustion engine, which states that for each omega, that is angular velocity of the internal combustion engine, there is one optimal, therefore there is one optimal power. So from this, it gives the angular velocity of the internal combustion engine as a function of power demanded, which multiplied by the beat radius and the angular velocity of the internal combustion engine. But here, the vehicle speed depends upon the battery engine operating line and instantaneous tau CVT value. So this is the powertrain parameters and fuel economy. Then battery parameters and energy economy. So here battery management system also plays an important role in the energy economy. So battery parameters are taken into account. Here the battery cells are connected in series in the first picture. Here the battery cells are connected in parallel in the second picture. So these are the proper cells and four cells are connected in series. As we all know, in series connection, the current is same, but the voltage is different. So the voltage across the first cell is 3.6 volt. The voltage across the second cell is 7.2 volt. The voltage across the third cell is 10.8, and the voltage across the last cell is 14.4 volt. So the current is same, that is around 3,400 milliamps Henry. So there will be a fault in the third cell, that is this cell contains a faulty cell. So, so it is the full voltage is not available to the electric vehicle. Here there are cells connected in parallel. Here there are also four cells connected in parallel. In parallel, the voltage is same, but the current is different. So the first cell comprises of 3.6 volt and the current is 3,400 milliamps Henry. And the second cell capacity is 6,800 milliamps Henry. And the third cell capacity is 10,200 milliamps Henry. And the fourth cell capacity is 13,600 milliamps Henry. The voltage across this four cell is 3.6 volt. The second cell, the second picture has faulty cells in the third battery. So that is 8,500 milliamps Henry capacity. So here also the full capacity is not available in the parallel connection. So here the cells are connected both in series and parallel. So here the first unit consists of 6,800 mAh battery and 3.6 voltage. The second cell, the second unit comprises of the same value, but the voltage is 7.2 volt. Here the Tesla has 85 kilowatt hour battery with 7104 cells with 96 cells in series and 74 cells in parallel. Here each operating mode has advantages and disadvantages, but control map are the best. The continuous variable transmission, belt strength, constraints vary. The electric motor allows for a reduction in the size of the internal combustion engine, which shuts it down under non-efficient conditions. So, if non-efficient, so the internal combustion engine of the electric vehicle shuts its characteristics under non-efficiency conditions. So these are the EV details. So the first column is EV make, the second column is battery capacity, the third is range, the fourth column is watt per kilometer. So while taking BMW i3, so that is 2019 model, so it consists of 42 kilowatt hour battery capacity, range is 345 kilometer, and water per kilometer is 165. So next, GM's part. So the battery capacity is 21 kilowatt hour, and the range is 120 kilometer. In watt-hour per kilometer is 175. So the next model is Honda Fit. So it comprises of 20 kilowatt hour battery, 112 kilometer range, and 180 watt hour per kilometer. So while taking Nissan Leaf Make, so 30 kilowatt hour battery range and 160 kilometer range, then watt hour per kilometer is 190. So while we consider Mitsubishi MI-EV, so the battery capacity is 16 kilowatt hour and the range is 85 kilometer and watt hour per kilometer is 190. Then we consider Ford Focus. So the capacity of the battery is 23 kilowatt hour and the range is 110 kilometer and watt hour per kilometer is 200. Then Mercedes Benz, the capacity of the battery is 28 kilowatt hour and the range is 136 kilometer and watt hour per kilometer is 205. While we take Tesla 3, the battery capacity is 75 kilowatt hour and the range is 496 and watt hour per kilometer is 151. So the hybrid electric vehicle must have an electric system that feeds the electric motor. So then lithium ion battery economics. So the battery parameters and battery management system also plays an important role in optimizing the powertrain for maximum energy economy. So here, while we consider lithium ion battery, the lithium required is 0.15 to 0.30 kilogram per kilowatt hour for 10 kilowatt hour capacity. Lithium cost is 1200 per kilogram. So if we consider 2 kilogram, the cost of the lithium is 2400 rupees. So lithium ion battery cost involves 12,600 kilowatt per kilowatt hour, that is in the year 2018. So that is for 10 kilowatt hour capacity. So 1,26,000 rupees is for lithium ion battery cost. The energy density is 130 watt per kilogram. So that is for 10 kilowatt hour, 75 kilogram is considered. So this is about the lithium ion battery economics. So these are the problems in battery. So the problems are oxidation of cell components, cathode breakdown, pressure buildup, electrolyte breakdown, separator melts, over temperature. So these are some of the problems occurring in battery. Also, there are battery parameters problem, overcurrent and due to over voltage and due to low voltage and low temperature. So the battery must be safe enough under overcharging or under undercharging. So consequence, so due to oxidation of cell components, the consequence is thermal runaway. And due to cathode breakdown, the consequences, the release of oxygen is occurring. And due to pressure buildup, there will be possible rupture in the battery. And due to electrolyte breakdown, flammable gases released due to the problem of electrolyte breakdown. And due to separator melts, the short circuit or overheating occurs. And due to temperature increase, there is a layer breakdown in the battery. So these are some of the consequences due to these problems in the battery. So also due to overcurrent, overheating will be occurring, and due to over voltage, overcharge or overheating will be occurring. So due to low voltage, anode dissolution will be take place, and due to low temperature, lithium plating is also taking place. So these are some of the parameters are taken into account for proper battery management system. So action. So problems are there and consequences are there. We have to take the action. So for these problems in the battery. So some of them are containment, then crusher vent open, then internal CAG open, then proper battery management system. Then for preventing from damage, we have to build up the battery or fuse. Then proper battery management system. So these are the recoverable damage and these are the irrecoverable damage. Then battery charging. So the main elements of the system are electric motor, which can work as generator, alternator, power electronics control unit, and a battery pack. So the battery selected here is lithium ion because of its successful use in commercial hybrid electric vehicles. And the battery pack and the alternator must be able to feed the top electric motor demand of electricity. Here, the charging should be to charge the batteries. The amount of power used for this is need to be considered and the device to be used. The goals of the charge strategy proposed are to keep the SOC between the limits desired to not to exceed the peak battery charge power, to increase the useful battery life, to operate the internal combustion engine close to its battery engine operating line when charging batteries, and to avoid starting the internal combustion engine only to charge batteries. So with the regenerative braking, it is expected to recover as much energy as possible without overcharging the battery pack. So here the charging strategy comprises of 5 types. So that is regenerative braking, that is between PT less than 0 and SOC less than the limit. And due to SOC less than this, the charging C1 takes place, that is it is in the level 1 and 2 charging station. So here AC charging system power flow, and this is the level 3 charging station. Here the DC charging system power flow. So here AC and here the level in the level 3 DC charging station takes place. So this is the battery charging, and in order to achieve efficient power distribution between the fuel cell and energy storage devices, a variety of energy management strategies have been proposed in the state-of-art literature. Here, the rule-based energy management methods have been developed for the hybrid vehicles such as saturation control, integrated rule-based heuristic method, and frequency domain power distribution finite state machine method. These energy management strategies distribute the energy between power sources based on their frequency characteristics. In spite of robust and real-time capable characteristics, the designs of such control strategies require knowledge about the system behavior and they cannot achieve optimal control. In order to enhance the performance of energy management system for fuel cell vehicles, optimal control strategies are attracted great interest due to their ability of achieving an optimal solution. They can be categorized as global optimal and local optimal. The most widely used algorithms are dynamic programming, genetic algorithm, and particle span optimization. Here, genetic algorithm, that is multiple objective genetic algorithm, is a traditional optimization method, and many advanced evolution algorithms have been proposed recently to enhance the optimization performance and also charging infrastructure. Here, a configuration of the regenerative system for construction equipment and energy management strategy are proposed to reduce the fuel consumption and to increase the battery performance. In addition, while most of the previous optimization-based fuzzy energy management systems only focus on the single objective optimization problem, such as fuel economy or efficiency enhancement, but this multiple objective optimization aims to increase the battery state of charge and fuel consumption reduction and the fluctuation of the fuel cell, and to save the operating cost and prolong the lifetime of energy source devices. So the objective function is comprised of 4 parts. The first part is the function of fuel economy, which is used to minimize hydrogen consumption. The second and third parts aim to maintain the SOC of battery and supercapacitor in suitable bounds to prevent overcharge or undercharge. And third is designed to smooth the response of fuel cell power and maintain it with high efficiency region. Here it is assumed that the EV scenario assumptions that most of the total non-commercial four-wheelers will be EVs and each will be having a capacity of 75 kilowatt hour as battery energy systems. Here the charger specifications. This company, that is ABB, has recently launched its tera-high power DC fast charger which can charge a vehicle with impressive of 350 kilowatt power. Considering latest and impressive technology, it is assumed that this technology will be the most preferred charging option at the commercial charging stations in the forthcoming years. Therefore, the ABB DC fast charger is considered for the present analysis of the EV penetration on Indian distribution grids. Using this charger, four-wheelers of 75 kilowatt hour capacity can be charged in around 15 minutes. So fast charging capacity is done. Four-wheelers of 110 kilowatt hour capacity can be charged in around 25 minutes. Heavy vehicles of 350 kilowatt hour capacity can be charged in around 60 minutes. Two-wheelers and three-wheeler EVs will be charged from home with 5 amps power socket. Four-wheeler EVs will be charged at home with 20 amps power socket. So these are the fast charging availability is there, and Swiss company has recently launched this technology. So these are the powertrain parameters in energy transformations. So here RST is decreasing, whereas the tau CVT, that is continuous variable transmission, is increasing according to the wheel torque. So these are the powertrain parameters in energy transformations. So these are the variables that play a role in energy transformation. N, RST, that is resistance of the simple train, then torque of the continuous variable transmission, then torque of the combustion engine, and charging capacity of the continuous variable transmission. So N here takes the range of 4. So in order to lower tractive effort of the belt, and the top range value is limited by manufacturing. Then resistance of the simple train ranges from 0.5 to 1 to increase the torque of the wheels. And tau CVT that lies in the range 0.5 to 2.5, not to increase tractive effort of the belt and couple angular velocity of the internal combustion engine with angular velocity of the wheels for different drive demands. Then tau CEM to modify the hybrid electric vehicle's top speed where the electric motor can assist with the power capacity. Then CCVT that is lies in the range 0.5 to 0.6 to lower the tracking effort of the belt and stay within the manufacturing and the available space. So powertrain parameters in energy transformation. So here in the petrol consumption is slowly decreasing as we are going for electric vehicle technology. So here the charge is decreasing after this, and here charge is increasing. Here charge is sustainable in the battery charge of 18 watt hour. So here the fuel consumption is also reducing. The battery management is lies in the safe operating limit, as well as the braking and idling losses are extremely low in urban driving and even lower in more congested driving, example within urban ports during rush hour or peak hours. Here the braking loss represents 26% of all the tractive losses in urban driving. Then idling losses represent about one-sixth of the fuel energy through this cycle. The losses to aerodynamic drag, a fifth or less of tractive losses in urban driving or less than half of the tractive losses during highway driving. So these are the energy transformations due to optimization of powertrain components. So these are the simulation tools used here, and I have used the MATLAB Simulink for powertrain optimization. So you can try for these simulation tools. So these are the EV manufacturers in India 2020. So Ola is going to launch 10,000 e-rickshaws in the year 2021 or 2000 by 22. They are setting up their they are setting up the charging stations in the near future. So Tata Motors entered into the EV manufacturing unit, then Mahindra Electric, Hyundai, Hero Electric, Kia Motors, and Ashok Leyland. So these are the top manufacturers, that is EV manufacturers in India. So in future, cars won't be called as cars but cows, that is computers on wheels. So my acknowledgement. So due to the inventors of internet, that is to Robert Econ and Windsurf, then Larry Page and Sr.G. for Google inventor, then copy and paste inventor Larry Tesler. So my sincere thanks and acknowledgement to these personalities. So kindly save energy and save the world. Thank you. Participants, if you have any queries, kindly interact.
Participants, if you have any query, you can ask our resource person. So if there are no questions, we would like to thank Revathi ma'am for her wonderful session on drivetrain technology for electrical vehicles. We were very much happy to listen to your words, ma'am. Maybe we will get one more chance to listen to you on another occasion. Thank you, ma'am. We'll end the session now, ma'am.
Thank you, sir.
Thank you, ma'am.